Good morning, I am Sheetal from BSc Chemistry Honours second year. Today I am going to make an audio recording for visually impaired student of inorganic chemistry book. Chapter name is Actinides. As we have learnt in chapter first, F block element constitute of two series of element placed at the bottom of the periodic table. These two series are lanthanide and actinide, which involve the filling of 4F and 5F subshell respectively. We have studied the chemistry of lanthanide in chapter 4. Let us now discuss the chemistry of actinide. Actinides, the 14 element which follows actinium from thorium to lawrencium in the periodic table are called actinides. These are analogous to lanthanide, involve the filling of 5F orbitals. As in case of lanthanide, the name of the series is after the name of the preceding element actinium, with which these element closely resembles. These are also called actinones. Before 1940, only the naturally occurring actinide, thorium, protonium, and uranium were known. The remaining elements are made artificially by nuclear bombardment. These elements are also known as man-made elements. Since these man-made elements have atomic number higher than U92. They are sometimes called trans-uranium element. Indeed, now man-made transition element constitute about 50% of the known chemical element. All the actinium are toxic to humans. These elements are radioactive and therefore the isolation and characterization of these elements, particularly the heavier ones, poses many problems. The individual elements are not produced clearly in the isolation, but must be separation from other actinide as well as lanthanide produced simultaneously by fusion. Their study posed serious problem due to the following reason. First is the decay process, that emitted particles are extremely energetic, which break bonds and rupture crystal structure. Second is the breaking of bonds by emitted particle in the sample of radioactive element is similar to continuous self-reduction process. Therefore, it is difficult to prove the existence of an oxidation state for every radioactive isotope. Third is the energy given out that appear largely as heat in sample. For example, the heat produced by a millimolar solution of curium 242 salt in water would be sufficient to evaporate the solution to dryness in short time. The radioactive nature have been two serious operational consequences. First is because of radioactive nature, it is necessary to employ elaborate radiation shielding, and therefore in many cases operation must be carried out by remote control. Second is the heavier elements are produced only in very small amount. For example, Mendelians was prepared in almost unbelievably small amount of the order of 1 to 3 atom per experiment. Therefore, it is very difficult to isolate and characterize these elements. However, the advancement in research and development of sophisticated instruments have made the chemistry of actinides as fascinating subject. General characteristics of actinide. First is electronic configuration. The actinide involve the filling of 5F subshell. Actinium have the electronic configuration 617s2. From thorium onwards, 5F orbitals get progressively filled because of the almost equal energy of 5F and 60 subshell. There are some uncertainties regarding the filling of 5F and 60 subshell. The electron may enter either of the two subshell. Therefore, there is double doubt whether thorium contain 5F electron or not, and two electron configuration are suggested for thorium, that is 5F062 7s2 or 5F161 7s2. Because of these uncertainty, different workers have suggested different configuration. The most widely accepted configuration of the element are given in table 1. The general electronic configuration of actinide may be written as 5F1 to 14 60 0 to 17s2. Physical properties. First is melting and boiling point. The melting and boiling point of actinide are moderately high, but they are considerably lower than those of transition element. However, there is no regular trend in melting and boiling point. Second is density. The densities of actinides first increase and then decrease as shown in figure table point 2. Third is heat of fusion and heat of vaporization. The heat of fusion and vaporization is measured only for a few elements. The heat of vaporization in generally decrease from thorium to Am. Oxidation state. Actinide shows +2, +3, +4, +6 oxidation state. However, +3 state is most common among all the actinides. The different oxidation state of actinides element are given in table 3. Some of the important conclusions regarding oxidation state of actinides are summed below. First is all the actinide have oxidation state +3 like lanthanide, but there is always not stable most oxidation state in actinide. For example, for the first four transitions, 4 element +3 is not the most stable oxidation state. It have been observed that the most stable oxidation state of the element up to uranium is one involving all the valence electron. For example, the most stable oxidation state of TH PnUr +4 +5 and +6, though Neptunium forms +7 oxidation state using all the valency electron, but this is oxidizing and most stable oxidation state of Np is +5. Second is plutonium shows all the oxidation state from +2 to +7, but the most stable state is Pu +4. Similarly, americium shows all the oxidation state from +2 to +6. However, for Am, the most stable oxidation state is +3. For all the element after Am, +3 oxidation state is most stable. Ionic radii in actinide contraction, like lanthanide, actinide also show actinide contraction. The size of the atom or ion of actinide decreases regularly along the series with increase in atomic number from actinium to lawrencium. The steady decrease in ionic radii with increase in atomic number is called actinide contraction. The actinide contraction is due to the imperfect shielding of one 5f electron by another in same shell. Therefore, as we move along the series, the nuclear charge and the number of 5f electron increase by 1 unit at each step. However, due to imperfect shielding of 5f orbital, the effective nuclear charge increase will result in the contraction of the size. Fifth is magnetic property. The magnetic property of actinide are lesser than that of theoretical predicted value. This is attributed to the fact that 5f electron of actinide are more exposed to crystal field and therefore are less effectively shielded. This results in quenching of the orbital contribution. The magnetic moment of tripositive actinide decreases from U3 positive to give a minimum at Pu3 positive, after which it increases and shows a maximum of Cf3 positive. Thereafter, it starts decreasing again as shown in figure 2. Color of ion. Actinide ions are generally colored. The color of actinide ion depends upon the number of 5f electron. The ion containing no 5f electron or 7 5f electron are colorless as expected. The ion containing 2 to 6 electron in the 5f electron are colored. The color arises out of electronic transition between various energy states within the 5f subshell FF transition. Formation of complexes. Like lanthanide, actinide also form complexes. However, actinide have great tendency to form complexes in comparison to lanthanide. This is because of high charge and small size of their ions. They form a wide range of complexes in different oxidation state of actinide. For +3 oxidation states, where there is much resemblance to lanthanide, octahedral coordination and coordination number 9 are found. For +4 oxidation state, coordination number 8 is very common. In +5 oxidation state, the ACF8 3 negative ion have cubic coordination number with +6 oxidation state. The hexafluorides are strictly octahedral. The general tendency to complex ion formation is controlled by ionic size and charge and decrease as M4 positive greater than MO2, 2 positive greater than M3 positive greater than MO2 positive. For an ion, the order of complexing ability is generally uninegative F negative greater than NO3 negative greater than Cl negative greater than ClO4 negative, binegative CO32 negative greater than OX2 negative greater than SO42 negative. Reactivity. The actinides are electropositive and very reactive metal. The reactivity increase with increase in the atomic number. The direct reaction of actinide with oxygen, halogen and acid are similar to those of lanthanide. They react with halogen to form non-stoichiometric hydride with the formula MH2 or MH3. They readily transition in air, forming a coating of oxide which is protective in the case of TH but less so for other elements. These metals react with most known metals, especially when heated. They resist attacks of alkaline and are less reactive toward acid. The chemistry of actinide is mainly concentrated on U and to the lesser extent on TH and Pu. Compound of actinide. Actinide form many compounds with known metals. Some of the important compounds of actinide are discussed below. Oxide and chalcogenides. Actinides forms oxide in different oxidation state +2, +3, +5 and +6. Oxides of actinide are refractory material. THO2 has the highest melting points of the oxides. These have been extensively studied because of their importance as nuclear fuel. Dioxide are known for almost all actinides. These are generally prepared by ignition of appropriate oxalates or hydroxide in air. The exception are CmO2 and CfO2, which require oxygen rather than air, and PaO2 and UO, which are obtained by the reduction of higher oxide. For example, UO2 is obtained by reduction of U3O8 with CO. It has black reddish brown color. The only anhydrous trioxide is UO3. It is obtained by heating uranyl carbonates or uranyl nitrate at 400 degrees Celsius. Among the tetrahalide, tetrafluoride are known for element up to Cf. These are formed by heating the dioxide in HF in the presence of H2 or O2. These can be prepared by heating the corresponding trifluoride with F2. In all these cases, metal is 8 coordinated, having slightly distorted square anti-prismatic array of F negative ion. The tetrachlorides are prepared by heating the dioxide in CCl4 or similar chlorinated hydrocarbon, whereas tetrabromide and tetraiodide are obtained from the element. The trihalide of all element U2Es are formed. Occurrence and isolation of actinide element. All the actinide elements have unstable nuclei and undergo radioactive decay. Among the half-lives of TH, UU and possibly of PU are such that they remarked on the Earth since the formation of the solar system. TH and are by no means rare and make up 8.1 ppm and 2.3 ppm of Earth crust respectively. These are in fact more abundant than tin. Occurrence and extraction of uranium. Occurrence: uranium occur in the following metal mineral pitch blend contains mainly uranium as U3O8 along with complex silicates of uranium Ra, TH, Pb, Bi, etc. Carnotite K2O.2UO3.B2O5.NH2O, Atunite, calcium carbonate. Extraction of uranium. The main source of uranium is pitch blende. It is extracted through the following step. First is concentration. The pitch blende ore is crushed to the fine powder and concentrated by gravity separation method to remove unwanted lighter impurities. Roasting. The concentration ore is roasted in the reverberatory furnace in the presence of excess of air to remove sulfur, arsenic, and other volatile impurities. The roasted ores, which contain U3O8, is fused with sodium carbonate and sodium nitrate. The whole mass is then heated to fusion, resulting in the formation of sodium uranate. Leaching with sulfuric acid. The fused mass is leached with dilute sulfuric acid so that sodium uranate change into the soluble uranyl sulfate, while impurities such as PbSO4 and RaSO4 remains insoluble and filtered off. Treated with sodium carbonate. The sodium solution is treated with an excess of sodium carbonate when impurities such as aluminium, nickel, cobalt, manganese get precipitated as basic carbonate, while uranium remains in solution as sodium tricarbonate uranate. Fifth is treatment with sulfuric acid. The insoluble carbonates are filtered off in solution of neutralized with dilute sulfuric acid and evaporated to dryness. When sodium diuranate Na2U2O7 is obtained as a heavy yellow precipitate. Sixth is treatment with ammonium carbonate. The yellow precipitate of sodium diuranate, it is digested with ammonium carbonate, resulting in the formation of soluble ammonium uranyl carbonate. The insoluble impurities are filtered off. The filtrate is boiled when lemon yellow crystal of ammonium diurate are obtained. On calcination, ammonium diuranate gives uranium oxide. Alternatively, the roasted ore is heated with dilute sulfuric acid for about 16 to 24 hours in the presence of oxidizing agents such as MnO2. The oxidized the U3O8 present in the roasted ore to insoluble uranyl sulfate. When the ammonium carbonate is added to the solution, ammonium uranyl carbonate is crystallized out, which is ignition gives U3O8. Comparison of actinide and lanthanide series. Both lanthanide and actinide involving the filling of 5f orbital. They show close resemblance in some of their property but also differ in many properties. Some of the important points of similarity and differences are summed up below. Similarities between lanthanide and actinide. Both exhibits oxidation state of +3 of predominantly. In both the series, f orbital are being progressively filled. Actinide and lanthanide have same number of unpaired electrons, have quite similar spectra. In the absorption spectra of element of both the series, sharp line-like band appear due to the FF transition. Both the electropositive and have high reactivity. Like lanthanide contraction, there is actinide contraction. These contractions are due to the poor shielding of 5f and 4f electron in actinide and lanthanide respectively. 6 is the nitride perchlorate sulfate of trivalent actinide lanthanide soluble, whereas the hydroxide fluoride carbonate of element of both the series are insoluble. Seventh is actinide. Like lanthanide shows an ion exchange behavior. Difference between lanthanide and actinide. Oxidation state. Lanthanide shows mainly +3 oxidation state except of few cases +4 and +2. +2 and +4. In addition to +3 state, actinides also show higher oxidation state such as +4, +5, +6 oxidation state. Both have large energy gap between 4f and 5d subshell. Due to the small energy gap between the 5d and 6d subshell, there is variability in the chemistry of the element. Binding energy of 4f are higher. Binding energy of 5f are higher. Lower. Shielding effect. 4f electrons have great shielding effect. Therefore, the contraction in their ionic radius is less. Therefore, 5f electrons have poor shielding effect. Therefore, the contraction in their size is more. Tendency to form complex Lanthanides have very less tendency to form the complex, whereas actinides have very high tendency to form the complex. Basic character. Lanthanide compounds are less basic. Actinide compounds are more basic. Tendency to form oxides. Lanthanide do not form oxides, whereas actinide forms oxides. Radioactivity. Except pre-methium in lanthanide, there is lanthanide are non-radioactive. All the actinide are radioactive, colorless. In case of lanthanide, most of their ions are colorless. In case of actinide, most of the actinide ions are colored. Paramagnetic characters. Lanthanide are paramagnetic and their magnetic property can be easily explained, whereas in case of actinides, they are also paramagnetic but their magnetic property cannot be easily explained.